Hello everyone. Today we are doing a basic hydraulic calculation and it's going to be a simple problem. Um, we won't be doing any derivations, but we will be making some assumptions along the way. Also, this is for those who are new or a little bit familiar with hydraulic calculation. If you do have questions or if you think that I've missed something along the way, please do let me know. Comment down below whatever it is so we can have it changed and have this corrected. It's greatly appreciated. So without further ado, let's jump to the problem. Here you go. All right, so we are to determine, this is a problem, we are to determine the flow in gallons per minute and total pressure in the cross main at the point indicated. So this is our schematic diagram. This is a floor plan that we are given. The circles that you're seeing here are sprinklers. This is the cross main. These are the branch lines. And again, we are to calculate up to this point. So one way of knowing that you've understood the problem is that you're able to properly label your schematic. So, and that's just what we're going to do. Before doing so, and before I forget, we're also provided with a table wherein where we have to put our solved values. It's gonna come handy as we progress with our solution. Okay, back to the problem. We're provided with a known parameters, so the classification of our occupancy in the problem is light hazard. There are different hazards. They're light, ordinary. Um, it depends on the occupancy. Um, there's the sprinkler density. It's 0.10 gallons per minute per square foot. Area cover per sprinkler is 90 square foot. Sprinkler constant K, which is 4.75. It's given. It actually depends on what type of sprinkler you will be using in your sprinkler system. That can be found in the manufacturer's technical data sheet that's provided with the manufacturer, of course. The distance between sprinklers, so this one here to this one, or this one to this one, is 2.5 meters. The distance of sprinkler down to cross main, so this one to this one is 1.2 meters, and the distance between branch lines is 3 meters. So this is the branch line here, this is the branch line here. So again, that's 3 meters. Now, if I have to draw, I have to draw a rectangular side. Oops, wait. Okay. Now, this one here, I'll just change the color to red. Okay, this is apparently the remotest area in the floor. That's one of our assumptions. Before we proceed, I would also like to, I've got some notes about the different formulas that we will be using in our calculation. So this is just a summary that I've found in my notes. So first one is, it has been summarized to the flow out of an open sprinkler. So that's Q equals K multiplied by the square root of the pressure. Then the pressure to raise the water up, this is the pressure. It's equal to 0.4331 times the height, the elevation. Friction loss through a pipe. So from one point to another point in the pipe, this is the pressure loss. 4.52 times length times Q raised to the power of 1.85 over C times raised to the power of 1.85 times D raised to the power of 4.87. Now we'll be explaining, or we'll be looking into the details. We'll be defining these equations along the way, but as for now, these are the basic equations that we'll be using for hydraulic calculation. Okay, let's go straight directly to the problem again. And what you need to do first is you need to take a look at density area curve. Okay, um, I think you can just Google it. I've if you've noticed, you've got the density in gallons per minute. It's in English units, and this one is in SI. So I'll just have to like look at this part in the bottom, and our sprinkler, our area of sprinkler of operation in square foot is on the left side, and in SI it's on the right side. So we'll be using the left part and the bottom part of this graph. We're already provided with the density. If we go back to our problem, okay, if we go back to our problem, our sprinkler density is point 10 gallons per minute per square foot, and the classification is light hazard. That's also provided. So if we take a look at the curve, this is the light hazard here, and this is the density here, point 10. We are to look for the area of the minimum area of sprinkler operation. So if this is the light hazard, that's point 10. Now the minimum area of sprinkler operation is 1500 square foot. Now we're going to be using that as our minimum remote area. Now if you've noticed, back to our problem, um, this is one of our assumption is this part here is the remotest area in the sprinkler. Okay, it has to, ideally that has to be the 1500 the 1500 square meter area, but in this case, since we're only calculate up to this point, then we'll just consider this part here. One way of solving problems is that you need to properly label your schematic. Now apparently we have not done that yet, so what we need to do is we need to properly label our schematic, so it will be handy as we progress with our solution. So this is my sprinkler one. I'm gonna label that one 1. This is my sprinkler 2, 3, 4, 5, 6. We're gonna assume that this is symmetrical. If you're able to calculate up to this point, this is the remotest area. I mean sprinkler, by the way. Also, the point at the crossmain where it interacts with, it intersects with the branch lines. This point here, this one, and this one. These are called the nodes. We can label that as node A, node B, and node C. All right, what you need to do is you need to calculate the flow required at the most remote sprinkler. That's the first step that you need to do. The minimum, so we already know that the minimum remote area is 1500 square meters, and the area cover per sprinkler, the area covers your sprinkler is 90, right? To obtain the flow from an individual sprinkler, you may have to use this formula. All right, here you go. So QS is equal to AC times D, where QS is the flow from individual sprinkler and AC is the protection area of coverage for individual sprinkler. The D is density. Now we can solve this one. That's QS. Our protection area of coverage is 90 square feet, right? That's QS is equal to 90 foot square, and you multiply that with the density, which is the density is 0.10, so that's 0.10 GPM per square foot. So for QS is equal to 90 times 0.10, that should be 20 times 0.1, that should be 9, so that's 9 GPM. And we can actually have this um, placed in our tabulated here. Flow from most remote sprinkler. So we can put 9 GPM here because that's the first thing that you need to know. Now, it means to say that every minute, that's per minute, the most remote sprinkler has to just discharge 9 gallons. However, there's a note here from NFPA. It's also placed in the table already that um, per NFPA 13, no sprinkler may operate at less than 7 psi. So we have to satisfy this note here, and our sprinkler must have to be at 7 psi. Now, if you've remembered, one of our formulas is this, the flow out of a sprinkler. So we can use this formula here, this one, in order to check how much is the gallons per minute, the flow rate here, if our pressure is 7 here. If we can go back to our solution, okay, we can input that. Okay, we can place that Q is equal to K square root of the pressure. Now, we're already provided with the K. This is the sprinkler constant. That's 4.75. Multiply that by 7 psi. And this equation here, this will give us with a flow rate in GPM if the pressure is in PSI. I forgot to, I'm just gonna let you see the equation, the definition of the equation. This is from NFPA. Okay, here you go. Just you may want to have a look at this one. All right, I'm gonna put that here, and I'm gonna put this one. All right, here and here. Okay, so let's define the equation again. Q is the flow from the individual sprinkler. This should be in GPM. The sprinkler factor, again, you can find this in this table in NFPA 13 2007, but you can also have a look at the manufacturer's technical data for sprinklers. Now, the K is 4.75. This is given here, and the pressure should be equal to 7 psi. This is the pressure from an individual sprinkler. So if we get our calculator, it's 4.75 times the square root of 7 psi. So that's 12.57. So we put that here is Q. Oops, Q is equal to, how much was that again? 12.57 GPM. Now you can compare these two here in order to satisfy the condition of NFPA. Let's go get back to the given table. Um, in order to satisfy this note that no sprinkler will operate below 7 psi, the minimum flow for this sprinkler must be 12.57. Now, if we're going to use this 9 GPM, right? If we're going to use this 9 GPM, then this condition will not be met. Hence, with this, we need to use the minimum flow rate from the last sprinkler. So from this sprinkler here, this sprinkler, the sprinkler one, we need to use this flow rate, not this one, so that we can satisfy the condition that this sprinkler has to operate at least 7 psi. All right, now we can input that in our table here, that the pressure. Okay, so we'll input that in our table, that the pressure. This is the sprinkler location. This is 1, and its required pressure is 7. Now we can also place that 12.57 is the gallons per minute. The flow required, 12.57 is the flow required at sprinkler 1. Now, if you've noticed, there's the Q, the small Q, and the big Q. We'll define that along the way. All right. That's actually the if you, the long Q. or the big Q is actually the flow of the total flow in the system, while the Q, the small Q, is the flow from a single sprinkler. That's a single sprinkler. All right. The next thing that you need to do is, let me just get back to the problem. You need to calculate the friction loss from here to here. And if you've noticed, our this pipe here, this pipe has a diameter of 25 millimeters. That's in millimeters. That's about 1 inch. 1 inch is about 24.5, but we'll round that off to 25. I mean to 1 inch for easier calculation, and it's also the standard. All right. Um, we also know that the length of the this pipe. So from sprinkler to sprinkler, that's already given. That's distance between sprinklers is 2.5 meters. What you need to do, if you've recalled the formulas that we have to use, okay. So first, this one. The second is this. This is actually the Hazen-Williams friction loss formula. Now, you can find this formula in NFPA 13. I'm just gonna let you see the definition of this formula. You'll have a look. Okay, here you go. We're gonna put that in our solution. Let me just hide this formula and the problem. So, okay. So this is our formula. So you'll find the Hazen-Williams loss. This is the formula, and so PF is the total friction loss in piece of pipe. That's in PSI. Q is the total flow in pipe. L is the length of pipe. This should be in feet. And C is the C factor of pipe, and we can find this from NFPA 13. I've got the table here as well. You need to have it. I mean, at least you need to see it. Okay, this is one of our assumptions as well. It's not given in the problem, but we will have to assume that we will be using, as of now, let's just use this one for easier step. We'll just assume that the pipe that we are using for the system is galvanized, so that's C value of 120. Okay, now, so if we plug in the equation, this equation, I'm just gonna remove this one. Wait, I'm just gonna remove this. 1 second. I'm just gonna place that here so that we have some space. Uh, okay, this one. Now, if we input the values, so if we solve this, that's okay. So that's PF, and this is 1 because this is the friction loss from point. Okay, from this point to this point. This one. So again, we already know the length. We've got the diameter. That's the D here. We've got the flow rate Q, and we've got the value of C. All we need to do is to input that in our equation. So that's 4.52 times Q, which is, what's the Q again? That's, we've already placed that in our table. That's 12.57. So, oh, it's on top. So that's 12.57. That's in GPM. That raised to the power of 1.85 times the length, and the length is, it's the length again, that's 2.5 meters. 2.5 meters, 2.5 meters, if we convert that to feet, so that's feet. This should be 2.5 times 3.28. 2.5 times 3.28. So that's, oh, wait, 2.5, right? Let me have a look. 2.5. So here, distance between sprinklers. So that's 2.5 times 3.28. That's 8.2. So this is the length. So our length, this one here. So again, this equation here is this one. The length is 8.2. That's already in feet. C is 120 raised to the power of 1.85, and the diameter is, again, that was um, 1 inch, right? Now, before I forget, remember your pipe has a thickness, right? The schedule, one of our assumptions that we that's not given in the problem is that we were not provided with what type of pipe we have to use, and we've just chosen the galvanized with C value equal to 120. That's one of our assumption. Another assumption that we will be making is that the schedule of our pipe is schedule 40, like all the pipes in the system. The reason for that is we've got a table here. We will know it's table 38, schedule 40 pipe. So if we've got a 1 inch, we get to know the internal diameter. It's in inches, 1.049. And if you go back to our solution, the diameter here, this is actually in inches. Oh, I forgot to include that, but this D here is in inches. So that's the reason why we are assuming that our pipe is schedule 40 even at the cross main, and everything is galvanized. That's with the C value of 120. That's also, again, as I've shown earlier in the table. So this D here is okay. Remember, I've told you the diameter is 1 inch, right? That's the nominal diameter. What we will actually be using here is the actual inside diameter, because this is what will matter. That's 1.049. Let's get back to this table. Schedule 40 pipe with the size. This is the nominal diameter. This is 1 inch, so that's 1.049. This one. All right. So that's 1.049 raised to the power of 4.87. D equals 4.87. Okay, if we get my calculator here, we all input this. So that's 4.52 times 12.57 raised to the power of 1.85 times 8.2 times 120 raised to the power of 1.85 times 1.049 raised to the power of 4.87 raised to the power of 4.87. 0. Let's just make it at two decimal places. So that's 0.45. So our pressure loss here, PF1 is equal to 0.45 psi. Now we can put that in our table now. That's our PF. That's 0.45. That's in psi. Now we also have to assume in our problem that our sprinklers does not have any elevation in the cross main. So if this is our floor plan here, now, what I'm talking about is, say this is our branch lines. This is the cross main, this one. Now what I'm talking about is the sprinkler is just right here. Does not have any elevation in terms of in reference to the cross main. So that's our assumption. Otherwise, if we're assuming that there's an elevation, then we can use the formula, this one, to raise up the water, 0.4331 times the height. But our assumptions is that there won't be any elevation with our our problem. It's not given anyway. Okay, so C factor is 120. The length, I forgot to input that here, but the length was 8.2. That's in feet. There's no fitting. Um, the fittings here are also provided in the given tables already. So there is none, so we put 0 here. The total length is 8.2. Now this is what I'm talking about earlier. The nominal pipe size was 1. That's 1 inch. That's, if you take a look at the problem again, this is the nominal pipe diameter, 25 mm. So this is what I'm talking about. It's about 1 inch. However, its actual pipe size, that's the internal pipe size, that's the one that we are using in the formula. It's 1.049. Just to be sure. Okay, that's 1.049 here. 1 inch and 1.049 inches. Let's fill this out, everything. Now, the elevation is 0. The K factor was, again, that was 4.75, right? Let me double check our problem here. Yeah, it's 4.75p. That's the one that I've used. Oh, 4.75. Okay, let's go back one more time to our table. The pressure loss is actually just, this is in psi per feet. All you need to do is you divide the friction loss by the total length in feet. Oops. So this is equal to this one. We divide that by the total length, M13. So we've got a 0.055 pressure loss in sprinkler location. Okay, the next thing to do is the total pressure required at sprinkler 2 is, you just have to add all this values. So what we have to do is this one plus 0.45, so that's 7.45, and then we need to solve for the flow rate at sprinkler 2. That's still, again, the flow rate, the small q is the flow at a sprinkler, the opening of the sprinkler. So we can solve that. Since we already have the pressure, we can solve that using this equation here, this one. Now, we won't be defining that again because we've already defined that, but now we're in sprinkler. Sprinkler 2. So our Q there is equal to K times the square root of pressure. I'm just going to go right at this. This is 4.75 times square root of, what's the pressure again? Total pressure is 7.45. 7.45. That's in PSI. So this is the Q2. We'll just put that. Oops. This one is, this should be a small q. If we use our calculator, that's 4.75. 4.75 square root of times the square root of 7.45. And this is our answer. So that's 12.96 q, 12.96. Let's just make that 13 GPM. We input that in our table. It's 13 GPM, and in order for you to solve for the total flow rate at sprinkler 2, all you need to do is add this up. So that's what we're going to do. 12.57 plus 13, so that's 25.57. So our Q2, we already have Q2 at 25.57. Now the next thing we need to do is we're gonna fill this up here, or this one. Again, we are still at the sprinkler 2, so we have the value of K at 4.75, right? Then as mentioned earlier, all the pipe that we are using are all galvanized. So we already have that figured, the C value for all, and that's gonna be 120. Actually, let me just fill this up till node C, because we are to calculate up to node C. The K factor, that's only up until the sprinkler 2, because there's no sprinkler 3, 4 here. They're just symmetrical, so we can just use a flow adjustment later on. Now the length at First, the pipe size. Let's get back to the problem. So the length size is 32 mm. I've done the conversion earlier, and the 32 mm is about 25 or 1 1/4 inch. 25, 32 mm. There's 25.4 mm per inch, right? Now, if 32, if we, I'm just got my calculator. If we divide 32 by 25.4, that's about 1.25. So this is roughly 1 1/4 inch. Okay. Let's get back to our table here and put the nominal size of 1 1/4. Now the actual size, we have to take a look at our table. That's for the pipe. Okay, here you go. Our table for 1 1/4, this one, I'm just gonna use, oops, 1 1/4. So the internal diameter is 1.38, and we input 1.38 as our actual pipe size. That's the internal pipe size, the internal diameter. Now, we are also provided that there are no fittings and devices for sprinkler 2, so we'll put 0 here for the equivalent length. And the length from sprinkler 2, the length for the pipe, the length from this one to this one is given. This is a sprinkler to the branch line, so distance of sprinkler down to crossmain is 1.2 meters. 1.2 meters, same as this. 1.2 meters, we'll just have to multiply 3.28 feet per meter. So 1.2 by 3.28, that's 3.93. We'll input that in our equation, so that's 3.936. So the total length is only 3.936 feet. 3.936 feet. Now we can now then solve for the pressure loss through the pipe. Our equation for that is just this equation, this one. So PF2 is equal to 4.52. This is constant if you recall this equation here. 4.52 times Q. Again, this is the Hazen-Williams friction loss formula. It can be found in NFPA 13. So that's 4.52 times the Q. That's the Q. We place that in our sprinkler too. That's 25.57. So this one is 25.57, right? 25.57 raised to the power of 1.85 times the length, which is the total length, is 3.936. 3.936 all over 120, the C value, raised to the power of 1.85 times the pipe diameter, the actual internal diameter, which is 1.38. So that's 1.38 inches. And I'm not going to put the units because it's already a derived units, and we've um, we've made sure that our our units are consistent with what's in the definition of the formula. It's in GPM, feet, the C factor, and the D diameter, which is in, oops, I'm just gonna put this here. D is the actual diameter in inches. All right, PF2 is equal to, where's my calculator? Okay, here. Let me see what we can change here. So we won't have to input everything. So that's, this one is 3.936. 3.936. This one is 25.57. 25.57, and this one is 1.38. 1 point, oops. So let me review this one more time. 4 point, so this is 4.52 times 25.57 raised to the power of 1.85 times 3.936 all over 120 raised to the power of 1.85 times 1.38 raised to the power of 4. Raised to the power of 4.87. 4.87. Almost forgot that. Thank you, calculator. And we've got 0.21. 0.21 psi. Then we'll put that in our table, 0.21 psi, and same with sprinkler 1, we have 0 elevation because we are again assuming that there is no elevation of the sprinklers in reference to the height, in reference to the crossmain. All right. The next value we need to consider is the pressure loss at sprinkler 2, and that is just equal to the friction loss through the pipe all over the total length. Oops. So the friction loss divided by 3.96936 and 16. Okay, so that's 0.053. Okay, the next thing we need to consider, as if you've remembered earlier, as I've mentioned, the small q is, so we're already done with this part here, right? I'm gonna color this so that you can see it. The next part is node A. Now, if you can remember, as I've mentioned earlier, the small q is the flow out of the sprinkler. Um, Q is the total flow. This one, it should be the same because it's the flow. I'll just input that here, 12.57. But I've seen some old notes that we've left it 0 and this small q in 1. Anyway, at node A, since there is no sprinkler, there won't be any flow for small q there. However, the big Q will be the same as this one here. Is because if you take a look at our sprinkler, it's the flow required at the flow required. This is the flow required at this point. So what you need to do, all you have to do is just copy the flow here, node 2, and that's the flow here. The next thing we need to check is they need to fill this out. First is, I forgot this one, the total pressure at node A. Again, that's just the summation of the pressures at node 2. So all you need to do is add this plus this, and you've got the total pressure required at node A. Okay, we need to solve for this, but before we solve for the friction loss using the Hazen-Williams formula, we need to fill this out. This one. All right. The pipe size for node A, going back to the problem, it's 50 mm. So that will be 2 inches. Again, it's schedule 40. So go looking at our table, schedule 40. It's 2 inches. Our internal diameter in inches is 2.067. So we input that in our table, so that's 2.067. Again, that's in 2.067 going back to our table. That's nominal diameter of 2 inches has an actual internal diameter of 2.067. Okay, let's get back to, so we're done with this. Okay, there's a T for the fitting and devices here. We need to figure out the pipe equivalent length for this T. Now, if we go back to our table, we've got this part here that a T or cross for a 2 inch. This one as 10. This is the equivalent schedule 40 steel pipe length per NFPA 13. That's again, this can be found table 14.4.3.1.1. Okay, so we go back again to the fittings and devices. That's T and the diameter of nominal diameter of 2. All you need to do is look at this 2 inch here. Just gonna go ahead and use a brush. So this one, this one, and T, this one. All right, so it seems like we have a 10 here. Um, so if we put that in our fitting, the pipe equivalent length, that is 10 feet. Now the length, so the length of our from node A to node B, this is the distance between branch lines that's given in 3 meters. All we need to do is convert that 3, there, that's 3 meters times 3.28. I'll just leave you guys for the unit cancellation, the unit analysis, and let's just go directly with the 3.28 times 3. So that's 9.84. 9.84, or we'll just make that 10 inches. I mean 10 feet, about 10 feet. This is just for easier calculation on this part. Uh, so that's 10 feet, so a total of 20 feet. Okay, with these filled out, you're now able to solve for the friction loss at node A from node B to node A. Governing equation for it is the Hazen-Williams equation, this one. And we go to our equation. I'll just go and input the values right away, same as this. That's PFA is equal to 4.52 times this one is the actual flow, 25.57 is the same, 25.57 raised to the power of 1.85, that's the constant, times this is the length. So in our case, our length is, a total length is 20. So we put that here. All over C value is still 120. That's the reason why, guys, I'm using one of our assumptions is that all the pipes in our sprinkler system is galvanized, like everything. Of course that would change if depending on what, if you're going to be designing it with another material or different schedules, but as of now we're using same material for the entire sprinkler system. So this is 120 here, and that's 1.85. You multiply that with um, this is the internal diameter. So the actual internal diameter is 2.067. This is the total length. This is the actual diameter, 2.067, and we put that here, 2.067 raised to the power of 4.87. So PFA is equal to, where's our calculator here? Oh, there. This is the, so we will change this to 2.067, 120.185. We change this to 20 feet. We change it's the same, 25.57, 4.52. We enter, so we've got 0.15. So that's 0.15 psi. So this is our we input that in our table. This is our friction loss, 0.15 psi. Now, with this, we are able to calculate for our pressure loss, which is this one divided by this one, the total length. And we've got 0.008. We can convert that to 0.01, but let's let's be consistent with the number of decimal points in the pressure loss sections. Still the same. We've got 0 pressure required for the elevation, due to elevation, because there's no, that's the reference point, or crossmain. This one here, it's not applicable because there is no sprinkler. This is only for sprinklers, so we're done. Technically, we're done with this part. Okay, I'm gonna save this one. The next part is the Q. Now, going to another section in the sprinkler, the first thing you need to do is to calculate the total pressure. Now, all you need to do is just to add this up. This one plus this one. I can do an auto sum there, but just so you'd see it, I'm doing it this way. Okay, it's still not applicable. Now, if you've noticed, let me get back to the problem. We're already at node B, right? So we're already done with this part here, and we've went all through this here. Now, if you've noticed in our table, we've got a different pressure from 7.81 and 7.66, right? What we need to do, we need to calculate the small q here because we're already considering the sprinklers. We won't be calculating these 3 and 4 sprinkler because they are just symmetrical with 1 and 2. However, in order for us to do that, we need to use this formula. This is actually for flow adjustments. Since the pressure is increased at point B, at this point it is increased. So we need to know how much water will actually flow through the second branch line, through the second branch line here. This is the formula. I'll just put that on the left side, and we'll define this here. So the formula is this. This is the for flow adjustments. QA is QA or Q. This is actually Q adjustment is equal to QL times the square root of, okay, just this one. Q adjustment is equal to the Q is equal to QL times the square root of pH over QL, where adjustment is the adjusted flow. That's the QB, the small letter QB. QL is the flow in the low pressure line. So our low pressure line, if we go back to our table, this is the one. This is 7.66. I'm just gonna, and another, our high pressure line is this one. So this is the PTB, PTI and PTV. If we substitute the solve for QB, the small b, that's QL, or QL is equal to QA, right? From our table, this is 25.57. So that's 25.57, and the pressure of PTA, which is 7.66, 7.66 over 7 point, P high, over P low, P high, PTB, sorry. So this is the high, 7.66, that's 7.66 below. 7.66, we remove this one. Oops, remove this one. And that's 7.81. Because this is pH, the higher over the lower pressure. So that's 7.81 over 7.66. So we can now solve for QB if we have our calculator. That's 25.57 times the square root of 7.81 over 7.66. So answer is 25.82. How many decimal places is that again? So that's 25.82, right? 25, oops. So that's 25.82. The total Q here is just the summation. Oh, let me up the sum. Oops. Okay, that one. H18 to H20. Hang on, that's the reason why I don't like the auto sum in this one. So what I do should be the same, but this one plus this one, that's the same, right? I'm just I'm just not so sure if that's the same or not. But apparently it's we've got 51.39 for our total Q at node B. Now we need to fill this out, this part here, in order for us to solve for this one, the PF. Friction loss. Now the nominal size, if we go back to our problem, the nominal size of our pipe from node B to node A, node B to, I mean from nodes B to node C is 65 mm. So if we do the math to convert that to, that was 65, right? 65, okay, 65 mm. So if we do the math, that's, oh, I have not placed the value here. That's 25.82. Let me just put it here. 25.82. So, all right. So our next. So I've done the math earlier already. 65 mm is roughly about 2.5 inch. If you don't, I'm just gonna show you how the math so you would believe me, but that's 25 per inch. It's a mm, and my calculator is here. One, that's 65 divided by 25.4. This is roughly about, it's 2.55, so that's about 2.5. So yeah, this one, 2.5. Okay, we're just gonna delete this one here. We'll fill this out. Our nominal was 2, and that was 2, whoops, that was 2.5, right? Our actual size for it can be found in this table back to, and again, it's still schedule 40. 2.5 give us 2.469. This one, 2.5, oops, gonna use my brush, 2.5, 2.469. Just gonna put that directly in our table. That's 2.469. Okay. Now the length from node A to node B. Let's get back to the problem, and that's, oh, here from node B to node C. This length here, distance between branch lines is still 3 meters, so that's the same as distance at node B. Where's my, so that's, okay, what's my table? It's the same as 10. We've already done the math earlier, so that's 10. And the fitting is still the same T, so we'll put that at 10. So the total length is the same, that's 20, the same as the node A. And we can now solve for PF. Okay, solving for PF, it's the same as this. So that's PFB is equal to 4.52 times 25. How much was the Q again? 51.39. So that's 51.39. So this is the 151.39. Raised to the power of 1.85. So again, this for the formula for PF, or the friction loss through the pipe from node C to node B, is uh, this one, PF. 51.39 is the flow rate at node B, raised to the power of 1.85. And what's the 20 again? This is the length. The total length is still the same, that's 20. All over the C value of 120 raised to the power of 1.85 times, this is the actual diameter, which is this one, 2.469, 2.469 raised to the power of 4.87. So we've got now a value of our PFP is equal to 4.52 times this, oops, 2.469. We'll change this one, 2.469. We change it, it's the same, but this flow rate is 51.39. So our friction loss here is 0.23. That's in PSI. And we'll input that in our table, which is 0.23, and we've got no zero elevation, so we don't need any pressure requirement. Node B filled out. We're almost done, and we've almost done. We're already at node C. Now, solving for a small q is the same as the flow adjustments, because if you've noticed, it's just a symmetric design. I mean, it's from node A to node B to node C. Um, wait, where is my floor plan? Okay, so calculating QB, the small Q at node C, it's just the same as how we calculate node B, the small q at node B. We won't be calculating this individually, 5 and 6, though we can do that. However, another way again is to do the flow adjustments, because they're just on the same crossmain, right? That's actually, we are to calculate up to that point. Now, there's going to be another assumption here, because we don't know this part, this to here. This, let's say this, the length of this to the riser, say this is our riser. So say the length of this one in total, like say it's 100 feet. This 100 feet, this already includes like, um, I don't know, but that's just our assumption that from node C to its source, like up until the riser, um, its total length is 100 feet. We need to have that because it's the pressure required here for the friction to counter it's the frictional loss, basically the friction loss that needs to be countered at node C. So that's the pressure requirement for the friction loss. We need to know that since we're not given with the exact value for this length, then we'll have to assume that it's about 100 feet from this point to the riser. Okay, so calculating QC, all you need to do is do the flow adjustment. I won't be defining that again, but QC is equal to our low pressure line. It's still QA. Okay, let me just see the table. Our low pressure line would still be QA, and our Q at node A is this one, or you can also use this one as the low pressure line, node B. Okay, let me just add this two first. I forgot. Again, all the first thing that you need to do if you're jumping to another section, I mean to another node or sprinkler in your calculation, is you need to calculate the total pressure. So in this case, I missed that earlier, but I'll just go ahead and add this up. So it's 8.04. So this is going to be our higher pressure line, and we can either use as our lower pressure line this 7.81 with a flow rate of 51 point or 25 or 25 51.39. We can also use this one and this one. This is going to be our reference. Okay, so going back to our equation, Our Q, it's the same as this, 25.57. So again, this one is the Q at node A, 25.57, this one. And then we multiply that by the square root of the high pressure line, which is 8.04, 8.04 all over 7.66, this one. So again, this time this is the high pressure line because we want to know how much is this. This is the high pressure line. This is the low pressure line using 25.57 as our flow rate. Or again, as I've mentioned earlier, you can also use the 7.81 and 25.82. It will just give us the same a similar answer. Anyway, 7.66 it is. 7.66. All right, here you go. Here's our calculator, and that's 25.57 times the square root of 8.04 divided by 7.66, 8.25.57. So that's equal to 26.2. Which was that again? 26.2. 26.2. It's 26.2. I'm gonna input that in our table now. So 26.2. 26.2. So the total flow rate now at node C is just 51.39 plus 26.2. That's just the value. So we've got now a total flow rate of 77.59. We can make that as 77.6. The next thing that we need to do is we need to input the values here so that we can solve for the friction loss at node C. And again, I've written earlier the length that we have to consider, and we've assumed that to be 100 feet because we were not given with we were not given in our problem with the actual length. So we're just told to calculate up to node C, but they should have a length from the source to node C. Okay, let me just input the values here first, the nominal and the actual size. So going back to our floor plan, where's our floor plan here? So our floor plan diameter is the same as here. So if we go back to our table, we can just go ahead and copy this. So that's 2.2 and 1/2, 2.469. And we've got that. Next, we need to figure the equivalent length of the fitting. The fitting is given as and divided as 2 elbows. Now, the elbows, we go to our table. We've got an equivalent length for that. Okay, for a 2 and 1/2 nominal diameter of the pipe, 2 and 1/2, this one here, we can choose either 45 degrees, 90 degrees, or 90 degrees long turn. We'll just go ahead and choose either of these two and say it's a standard elbow, this one. So we can choose 6. Now, some 6 feet as the equivalent pipe length for a standard elbow. However, there are 2 elbows, so 6 times 2, that will be equal to 12. So our total length here is 112. Now, with these information, hang on, I forgot to solve for the pressure loss. Here, let's just solve that along the way. So that's PF all over the total length of 20. Okay, I've missed that. I'm sorry. Here, we can now solve for the PF with our assumption of 100 feet length with our total length solved. Our PFC using Hazen-Williams formula is just equal to PFC. Again, it's just like this, right? And this is just equal to, oops, This is just equal to 4.52 times the flow rate, which is 77.59 raised to the power of 1.85 times the total length. In this case, our total length is 112. So total length is 112 all over. C value is still the same, 120 raised to the power of 1.85. This is the diameter. It has the same diameter as we've copied earlier. That's 2.469. So that's 2.469 raised to the power of 4.87. So again, I'm just using the Hayes and Williams formula. We've already defined that earlier. So all right, where's my calculator? 4.52 times 77.59 raised to the power of 1.85, 77.59. Well, times 112, that's the length in feet, times the C factor of 120, raised to the power of 1.85 times 2.469 raised to the power of 4.87. I hope I did not miss anything. This actually, I'm just gonna review it because I don't want to to miss the calculation. Okay, that's 4.52 times 77.59 raised to the power of 1.85 times 112 all over 120 raised to the power of 1.85 times 2.469 raised to the power of 4.87. This is equal to 2.769 or 2.77. So we've got now our PFC, which is 2.77 is in PSI, and 2.77, we can input that in our table here. 2.77, we've got zero elevation. K factor is not applicable because we've got no sprinklers at node C. Oh, I forgot this pressure loss again. No, I'm not forgetting it, but that's 2.77 divided by the total length, and we've got 0.025. All right. I've got another table here. Okay, this is table 11.2.3.1.2. It's still in NFPI 13. We've got an occupancy of light hazard, right? We'll be using the total combined inside and outside hose in GPM. So we've got 100 GPM. So that's actually our inside and outside hose. All we need to do is input that here. That's the flow required. Hang on, this one, 100. So the total Q, all in all, is this plus this. So it's 177. So we don't have to fill this out here. The total pressure can be calculated from this one. Okay, hang on. Let me just put the equal sign. That's 8.04 plus 2.77. So that's 10.81. So here we go. So we've actually finished everything, guys. The total required that, I mean, the total flow rate required is 177.59. So the total flow rate is, where's my table again? 177.59. We'll make that 178. Q total is equal to 178 GPM. 178 GPM, and the total pressure is 10.81. Let's make that as 11 psi. So there you go. That's our final answer. It's a very long one. It's a simple step, but we have to let you see the step-by-step calculation. I hope that's gonna help you guys. If you have questions or if you think I've missed something again, please do let me know. Put that in the comment down below. and I'll see you in the next one. Thank you.